There is a dream that unites us as a species, a deep and ancient yearning woven into our oldest stories and our most modern fantasies. It is the dream of reaching the stars. Ever since we first looked up into the vast, silent darkness of the night sky, we have longed not just to understand those distant points of light, but to journey to them, to explore the worlds that might orbit them, and to find our own place in the great cosmic ocean. This primal impulse is the engine of our science fiction. It powers the starships that leap into hyperspace. It fuels the warp drives that bend the very fabric of reality, and it opens the stargates that promise instantaneous travel across the galaxy. These are beautiful, powerful fantasies, and they all express one fundamental human desire: the desire to overcome the tyranny of distance, to free ourselves from the immense, lonely gulfs of empty space that separate the worlds. In our real, physical universe, this grand and beautiful dream runs headfirst into a wall. It is a barrier erected by the most fundamental laws of nature, a cosmic speed limit that is woven into the very fabric of space-time itself. That limit, of course, is the speed of light. To travel at or beyond a speed of light is the holy grail of space exploration, the ultimate goal that would allow us to turn our science fiction into science fact. It would allow us to cross our solar system in a matter of hours instead of years, and to reach the nearest neighboring stars within the span of a single human lifetime. The question, therefore, is an inevitable and a timeless one. What would it take? Can we do it? Can we, a species of curious explorers, find a way to break this one ultimate law? Can you travel faster than light? The answer that modern physics gives us is a far stranger, deeper, and more beautiful one than any science fiction story could ever imagine. It is an answer that forces us to abandon our everyday common sense, to redefine our entire understanding of space, of time, and of the very nature of reality. It teaches us that a journey to the speed of light is not just a journey through space, but a journey through time itself, with consequences so profound that they challenge our own identity and the logical consistency of the entire universe. Tonight, we will embark on that journey, not in a ship of steel, but in a quiet vessel of the mind, guided by the strange and beautiful laws of Albert Einstein's theories of relativity. Before we ignite our imaginary engines and begin our acceleration towards this great cosmic barrier, I would love to know from which part of our quiet planet you are joining this journey tonight. Please write your city or country in the comments below. It is a wonderful way to feel our connection, a global crew of travelers, all sharing this moment of cosmic exploration. And if you enjoy these calm journeys to the very edge of our understanding, please consider subscribing to the channel. Your support is the gentle energy that allows these voyages to continue, always calmly, always at the pace of the universe. Our journey tonight is not an attempt to break the laws of physics, but an attempt to understand them in all their deep and quiet beauty. The true magic of this story, the real strangeness, is not in finding a way to travel faster than light. It is in discovering why this barrier exists in the first place. The universe, it seems, has a very good and very profound reason for imposing this speed limit. And in its quest to protect this one sacred law, it is willing to bend and warp its own most fundamental components. As we explore this topic, we will discover that as we approach the speed of light, time itself begins to slow down, and space itself begins to contract. We will learn that the price of reaching this ultimate speed is an infinite amount of energy, a price the universe itself cannot pay. We will discover the deep and logical reason why faster-than-light travel is forbidden, because it is indistinguishable from time travel and would unravel the very fabric of cause and effect. And then, Once we have understood the great and beautiful wall that stands before us, we will explore the speculative, theoretical loopholes that might one day allow us to cheat the law without breaking it. The strange and wondrous ideas of wormholes and warp drives. And so, let our journey begin, not with a burst of impossible speed, but with a quiet and patient first step, back to a time when our universe seemed a much simpler and more logical place. To truly comprehend the strange and beautiful revolution that Albert Einstein brought to our understanding of the universe, we must first take a quiet and deliberate step backwards. We must journey back to a simpler and more intuitive time, to a universe that felt far more like our own everyday experience. Before we can appreciate the new and often paradoxical rules of our cosmos, we must first immerse ourselves in the old rules, the elegant, logical, and common-sense framework that governed all of scientific thought for more than 200 years. This was a universe imagined and codified by one of the greatest minds in human history, Sir Isaac Newton. It was a universe that was, above all else, a place of profound and comforting order. Let us imagine the intellectual world of the late 17th century. Before Newton, the cosmos was still a place of deep mystery, a realm where the heavens and the earth were thought to be governed by entirely different sets of rules. The motions of the planets were the business of gods and angels, while the falling of an apple was a mundane, earthly affair. Newton's great and revolutionary genius was to unite these two realms under a single, universal set of laws. He demonstrated, with breathtaking mathematical elegance, that the same force of gravity that pulls an apple from a tree is the very same force that holds the moon in its orbit around the Earth, and the Earth in its orbit around the Sun. In a single brilliant stroke, he had brought order to the cosmos. The universe in Newton's vision was no longer a place of capricious and unknowable winds. It was a great and magnificent machine, a clockwork universe, which had perhaps been set in motion by a divine creator, but which now ran on its own, according to laws that were predictable, knowable, and ultimately simple. This beautiful clockwork model of reality was built upon two immense and seemingly unshakable pillars, two ideas that were so self-evident that they were considered to be absolute truths. The first of these pillars was absolute space. In the Newtonian universe, space was the fixed, unchanging, and infinite stage upon which the great cosmic drama unfolded. Imagine a vast, invisible, three-dimensional grid that extends forever in all directions. This grid was the ultimate reference frame for all of existence. It was rigid and eternal. The stage itself was completely unaffected by the actors and the events that moved upon it. This idea provided a deep sense of certainty. A meter was always a meter. A mile was always a mile. It did not matter who was measuring it, or how fast they were moving, or where they were in the universe. The fundamental geometry of the cosmos was the simple, flat, and reliable Euclidean geometry that we all learn in school. Space was the silent, passive, and absolute background of reality. The second great pillar was absolute time. For Newton, and for all of us in our daily lives, this idea feels even more fundamental than that of absolute space. Time, in this view, was imagined as a great, universal river, flowing forward at a constant and unchangeable rate for every single thing in the entire cosmos. Imagine a giant, invisible clock at the very center of the universe. A clock whose steady, rhythmic tick-tock was the same for a person resting on the Earth, for a sailor on a fast-moving ship, and for a being in a galaxy a billion light-years away. 1 second, for you, was precisely 1 second for everyone and everything else. This universal time was the great equalizer, the steady and reliable pulse that governed all of existence. It was the ultimate shared metronome of reality. This idea is so deeply embedded in our intuition that it is almost impossible for us to imagine a world in which it is not true. And from these two great pillars of absolute space and absolute time, a very simple and logical consequence followed: the simplicity of speed. In this common-sense clockwork universe, speeds were simply additive. This is a rule we use instinctively every day. Let us imagine you are on a perfectly smooth train, one that is moving at a steady 100 kilometers per hour. If you were to stand up and throw a ball forward down the aisle at a speed of 20 kilometers per hour, what would an observer standing on the platform outside the train see? They would see the ball moving at a speed of 120 kilometers per hour, the speed of the train plus the speed of the ball. It is simple, intuitive, and correct. And in the Newtonian dream, there was no reason to believe that light should behave any differently. If you were on that same fast-moving train and you turned on a flashlight, pointing it towards the front of the train, the light from that flashlight should, according to all common sense, travel at its own immense speed plus the 100 kilometers per hour of the train. In this universe, there was no such thing as an ultimate cosmic speed limit. The idea of traveling faster than light was not a violation of any physical law. It was merely a great and perhaps insurmountable engineering challenge. For more than 200 years, this beautiful, orderly, and deeply logical picture of the universe reigned supreme. It was a magnificent and successful dream. But it was a dream from which the world of physics was about to have a very strange and very wonderful awakening. We have been resting in our minds in the beautiful, orderly, and deeply logical universe of Isaac Newton. It is a universe that feels like home, a place of common sense, a great and predictable clockwork machine, where space is a fixed and rigid stage, and time is a great, universal river, flowing at the same steady pace for all. For more than 200 years, this magnificent vision of the cosmos was the unshakable foundation of all science. It was so successful, so powerful in its ability to predict the motions of the planets and to describe the mechanics of our own world, that by the end of the 19th century, many physicists believed that their work was almost complete. The great laws of the universe, it seemed, had been discovered. All that was left was to refine the measurements and to tidy up a few small remaining loose ends. In the year 1900, the great physicist Lord Kelvin famously described the state of physics as a beautiful, clear sky, troubled only by two small clouds on the horizon. One of those clouds had to do with the nature of heat and energy. The other, the one that concerns our journey tonight, was a small, nagging, and persistent puzzle about the nature of light. No one at the time could have possibly known that this one small, theoretical cloud was about to grow into a great and powerful storm, one that would tear down the entire beautiful clockwork edifice of the Newtonian universe. The story of this storm begins with the greatest triumph of 19th century physics, the understanding of light itself. The brilliant Scottish physicist James Clerk Maxwell had shown with his beautiful set of equations that light was an electromagnetic wave. It was a traveling disturbance in electric and magnetic fields, a self-propagating ripple that moved through the cosmos at an incredible and very specific speed. This was a revolutionary discovery, but it immediately created a profound and difficult question. Every other wave that humanity had ever known required a medium, a substance to travel through. Sound waves are a vibration of the air. Ocean waves are a disturbance in the water. A wave, by its very definition, is a disturbance in something. So, if light was a wave, and it could travel from the distant stars to the Earth through the apparent vacuum of empty space, then what was the medium that was carrying it? To solve this puzzle, physicists proposed the existence of a strange and wonderful, yet completely undetectable substance. They called it the luminiferous ether. The ether was imagined to be a massless, frictionless, and perfectly transparent substance that filled every single corner of the entire universe. It was the silent and invisible scaffolding of all existence. It was completely stationary, the physical embodiment of Newton's idea of absolute space, the one true, fixed reference frame against which all motion could be measured. And it was the medium through which the great waves of light traveled, just as the ocean is the medium for the waves of the sea. This was a beautiful and logical idea, and it led to a clear and testable prediction. If this stationary ether exists and our planet Earth is in constant motion, orbiting the Sun at a speed of some 30 kilometers per second, then the Earth must be moving through the ether. And if we are moving through this invisible substance, we should experience an ether wind. Imagine you are on a perfectly calm lake in a sailboat. Even if there is no wind, as your boat begins to move, you will feel a wind in your face, a wind created by your own motion. In the same way, the Earth, in its journey through the stationary ether, should be feeling a constant ether wind, and this wind should have a small but measurable effect on the speed of light. The light traveling in the same direction as the Earth, moving with the ether wind, should appear to be traveling slightly faster. The light traveling against the wind should appear to be traveling slightly slower. It was a simple, logical, and direct consequence of the entire Newtonian worldview. All that was needed was an experiment sensitive enough to measure this tiny, expected difference. In the year 1887, two brilliant American scientists, Albert Michelson and Edward Morley, built that experiment. It was one of the most elegant and clever experiments in the history of science. They used a device called an interferometer, which took a single beam of light and split it in two. It sent these two beams on journeys of the exact same length, but at right angles to each other, and then recombined them. If there was an ether wind, one of the beams, the one traveling against or across the wind, would be slowed down just a tiny fraction more than the other. And when the two beams were brought back together, they would be slightly out of sync, creating a specific pattern of interference, a series of light and dark fringes. By rotating the entire apparatus, they could change which beam was fighting the wind, and they should have seen a clear and predictable shift in this interference pattern. The device was so exquisitely sensitive, it should have been able to easily detect the expected ether wind. They set up their experiment in a quiet basement in Cleveland, Ohio, placing the heavy stone slab of their interferometer on a pool of mercury to dampen any possible vibrations. They held their breath, and they looked, and they found nothing. There was no shift in the pattern. They rotated the device. Still nothing. They tried at different times of day and at different times of the year to catch the ether wind from different directions as the Earth moved in its orbit. The result was always the same: a profound, stubborn, and complete null result. The most famous failed experiment in history was in fact an incredible success. It showed, within its exquisite sensitivity, no detectable ether wind, undermining the stationary ether hypothesis and supporting the constancy of light speed. And this left the world of physics in a state of deep and profound crisis. Light was a wave, but it seemed to have no medium, and its speed refused to obey the simple, common-sense laws of addition. The clockwork universe was broken, and the stage was now set for a new and revolutionary idea to be born. We have left the world of physics in a state of quiet and profound crisis. The beautiful, orderly, and common-sense clockwork universe of Isaac Newton, a scientific cathedral that had stood unchallenged for over 2 centuries, had been shaken to its very foundations by a single, stubborn, and inexplicable fact. The Michelson-Morley experiment, one of the most brilliant and sensitive experiments ever devised, had gone in search of the luminiferous ether, the invisible, absolute medium for light, and had returned with nothing. Its result was a paradox that seemed to have no solution. Light behaved like a wave, but it had no medium, and its speed, in a defiant violation of all logic and intuition, refused to change, no matter how fast its source or its observer was moving. The greatest minds of the era tried desperately to save the old theory, proposing complex, awkward, and ultimately unsatisfying patches to explain away this strange new reality. The clockwork was broken, and no one knew how to fix it. And then, from the quiet and obscurity of a patent office in Bern, Switzerland, a new and revolutionary voice emerged, a voice that would not only fix the clock, but would redesign the very nature of time itself. In his miracle year of 1905, a young and almost completely unknown physicist named Albert Einstein published a series of papers that would forever change the course of human thought. One of these papers, on the electrodynamics of moving bodies, contained what we now know as the special theory of relativity. Einstein's genius was not in his complex mathematics, but in his profound and courageous simplicity. Instead of seeing the baffling result of the Michelson-Morley experiment as a problem to be solved, he chose to see it as a clue, a deep and fundamental truth about the nature of the universe that had been there all along, just waiting to be recognized. He decided to stop trying to save the old, broken theory. Instead, he chose to build a brand new one from the ground up, a new vision of the cosmos built upon two of the most simple, beautiful, and powerful postulates in the history of science. The first of these great new pillars was the principle of relativity. This idea, in itself, was not entirely new, and it feels quite intuitive. It simply states that the laws of physics are the same for all observers who are moving at a constant speed in a straight line. We have all experienced this principle. Imagine you are on a perfectly smooth train, one that is not accelerating or turning, and the window shades are closed. There is no experiment you can possibly do inside your train car to determine if you are moving at 100 miles per hour or if you are standing perfectly still at the station. If you throw a ball in the air, it will go straight up and come straight back down into your hand. If you pour a cup of tea, the liquid will fall directly into the cup. The laws of motion and gravity behave identically in both situations. The profound implication of this simple principle is that there is no such thing as absolute rest in the universe. All motion is relative. You can only say that you are moving relative to the train station, or to the ground, or to a distant star. The universe has no preferred, absolute, and stationary reference frame. This one simple idea on its own was enough to sweep away the old, complicated notion of a fixed and stationary luminiferous ether. The second pillar was where the true revolution began. Einstein took the stubborn, paradoxical result of the Michelson-Morley experiment and elevated it from a strange anomaly to a fundamental and unbreakable law of nature. This is the principle of the constancy of the speed of light. It states that the speed of light in a vacuum is the same for all observers, regardless of their own motion, and regardless of the motion of the source of the light. This is the idea that breaks our common sense. Let us return to our train. In the old Newtonian world, if you were on a train moving at a high speed and you turned on a flashlight, an observer on the platform would measure the speed of that light as its own normal speed, plus the speed of the train. But Einstein's second pillar declares that this is wrong. It states that both you on the moving train and the observer standing still on the platform will both measure the speed of that very same beam of light, and you will both get the exact same number, approximately 300,000 kilometers per second. Here, in the collision of these two simple and elegant ideas, a new universe was born. How can this possibly be true? How can the speed of the same object be identical for two observers who are moving at different speeds? Speed, after all, is simply distance divided by time. If the speed of light is an absolute constant for everyone, then the only way for the equation to work, the only way for reality to remain logically consistent, is if distance and time themselves are not absolute. This was Einstein's great, courageous, and world-changing insight. He realized that to protect his two beautiful and simple postulates, he had to sacrifice the two great, intuitive pillars of the Newtonian universe. He had to abandon the ideas of absolute space and absolute time. Space and time, he realized, must be relative. They must be flexible, personal, and malleable. They must be able to stretch and to shrink, to conspire together in a beautiful and perfectly choreographed dance, all to ensure that the one sacred cosmic speed limit is never, ever broken. The rigid clockwork universe was gone, and in its place was a much stranger, more dynamic, and more wondrous woven fabric of spacetime. We have arrived at the dawn of a new and stranger cosmos. The elegant, common sense, and comfortable clockwork universe of Isaac Newton has been shattered by a single, stubborn fact: the strange, inexplicable, and absolute constancy of the speed of light. Albert Einstein, in his profound and simple act of intellectual courage, chose not to fight this fact, but to embrace it. He built a new universe upon two new pillars: that the laws of physics are the same for all observers in uniform motion, and that the speed of light is constant for all of them. Once we accept these two simple and beautiful ideas as the fundamental rules of our reality, a series of strange, wonderful, and unavoidable consequences must follow. The old, rigid stage of absolute space and the great universal river of absolute time must both give way. They must become flexible, personal, and intertwined. And the first and most famous of these consequences is the profound and beautiful idea that time itself is elastic. This is the phenomenon of time dilation. The core idea of time dilation can be stated very simply: the faster you move through space, the slower you move through time, relative to a stationary observer. This is not a metaphor. It is not a psychological feeling. It is a real, physical, and measurable property of the universe we inhabit. To understand why this must be true, let us join Einstein and conduct a simple and beautiful thought experiment. Let us imagine the most perfect and simple clock we can possibly build. This light clock consists of two perfectly parallel mirrors facing each other, with a single particle of light, a photon, bouncing between them. Every time the photon travels from the bottom mirror to the top one and back again, our clock makes one tick. First, let us imagine we are on our perfectly smooth-moving train, and this light clock is sitting on the table in front of us. From our perspective, we are stationary relative to the clock. We watch the little photon of light. It travels a simple, straight, vertical path up to the top mirror, and then a simple, straight, vertical path back down. The distance it travels for one full tick is just twice the distance between the mirrors. Its path is short and direct. This is the clock's normal, baseline rhythm. This is its proper time. Now let us imagine we are standing on the platform outside, watching this same train, with its light clock, speed past us at a significant fraction of the speed of light. From our perspective, the clock is in motion. We watch the same photon of light as it begins its journey. It leaves the bottom mirror, but by the time it reaches the top mirror has moved forward. So from our point of view, the photon has not traveled a straight vertical path. It has traveled along a longer, diagonal path. And the same is true for its journey back down to the bottom mirror, which has also moved forward. From our perspective on the platform, the photon in the moving clock is tracing a zigzag pattern. And here we arrive at the heart of the matter. We have two observers, one on the train and one on the platform. The observer on the train sees the photon travel a short vertical path. The observer on the platform sees the very same photon travel a much longer diagonal path. But, and this is the great, unbreakable, new law of our universe, both observers must measure the speed of that photon to be exactly the same, the constant speed of light. If the speed of the photon is the same for both of us, but the observer on the platform sees it travel a longer distance, then there is only one possible conclusion, a conclusion that shatters 200 years of physics. The time it takes for that event to happen must also be longer for the observer on the platform. From our stationary point of view, the moving clock is ticking more slowly. Time itself, for everything on that train, has slowed down. This is not a mechanical trick of our imaginary light clock. Because Einstein's first pillar states that all the laws of physics are the same for all observers, this slowing down must apply to every process. A quartz watch on the train would tick more slowly. The chemical reactions inside a battery would proceed more slowly. And most profoundly, the biological processes of a human body would also slow down. The beating of a heart, the firing of a neuron, the complex and subtle dance of cellular aging itself, all of these processes, which are governed by the same laws of physics, would be observed to be running in slow motion for a person on the train, relative to a person on the ground. This is not a theoretical paradox. It is a physical reality that we now use every single day. The satellites of the Global Positioning System, or GPS, are in orbit high above the Earth, moving at speeds of thousands of miles per hour. The incredibly precise atomic clocks on board these satellites tick at a different rate than clocks on the ground. Special relativity, because of their speed, makes them run slightly slower, while general relativity, because they are higher in a weaker gravitational field, makes them run faster. The net effect is that GPS satellite clocks run faster than ground clocks by a few dozen microseconds per day, and the system works only because engineers continuously correct for both effects. If the engineers who designed the GPS system did not constantly and precisely correct for this relativistic effect, the entire system would fail within hours, accumulating positioning errors of several miles every single day. Newton's great universal river of time does not exist. The universe, we must now accept, is filled with an infinite number of personal streams of time, each one flowing at a different rate, all depending on its own unique journey through space. We have just taken the first and perhaps most difficult step into the strange new reality of Albert Einstein. We have let go of the comforting and intuitive idea of a single, universal river of time. We have learned, through the beautiful and simple thought experiment of the light clock, that time itself is personal, flexible, and relative. The faster you move through space, the slower you move through time. This is the first great price the universe demands in order to protect the sacred and absolute constancy of the speed of light. But this is only half of the story. For time to be able to stretch and slow down, its partner in the fabric of reality, space, must also be able to change. Time does not act alone. To ensure that the cosmic speed limit is never broken, the universe must employ a second, equally profound and equally beautiful mechanism. We must now explore the second great consequence of special relativity, the idea that space itself is elastic. This is the phenomenon of length contraction. The core idea of length contraction can, like its temporal counterpart, be stated very simply. An object in motion is measured to be shorter in its direction of motion than it is when it is at rest, relative to a stationary observer. A spaceship that is 100 meters long when it is sitting on the launch pad will, when it is flying past you at a significant fraction of the speed of light, be measured by you to be perhaps only 80 meters long, or 50, or even 10. The very meter stick of the universe shrinks for things that are in motion. This idea, like time dilation, feels deeply counterintuitive. But it is not a separate or an additional effect. Time dilation and length contraction are not two different rules. They are two sides of the very same coin. They are the two perfectly synchronized ways that space-time itself must warp and conspire to ensure that the speed of light remains constant for everyone. One cannot exist without the other. To truly understand this beautiful and inseparable partnership, let us return to the real-world evidence we discussed in our last chapter, the strange and wonderful story of the muon. As we learned, muons are tiny, unstable subatomic particles that are created when high-energy cosmic rays strike the top of our atmosphere. They have an incredibly short lifespan, on average only 2.2 microseconds, which is just 2.2 millionths of a single second. Even traveling at nearly the speed of light, this is not nearly enough time for them to travel the many kilometers from the upper atmosphere down to the surface of the Earth before they should decay into other particles. And yet, we detect them here on the ground in great numbers. In our last chapter, we explained this from our own perspective as observers on the ground. From our point of view, the muon is moving at an incredible speed, and because it is moving so fast, its internal clock is running in extreme slow motion. Its tiny 2.2 microsecond lifespan, from our perspective, gets stretched out by time dilation, giving it more than enough time to complete its journey to the surface. This is a perfect and complete explanation. But now, to understand length contraction, we must perform the most important act in all of relativity. We must change our perspective. Let us imagine for a moment that we are the muon. From our new perspective, riding along with this tiny particle, we are at rest. Our internal clock is ticking at its normal, rapid rate. Our entire lifespan is, and will always be, just a brief 2.2 microseconds. From our own perspective, we are not experiencing any time dilation at all. And yet, here we are. We have been born in a flash of light in the upper atmosphere, and a moment later, we successfully arrive at the surface of the Earth. If our time has not stretched, how is this possible? The only way this journey can be possible in our incredibly short lifetime is if the distance we had to travel was not many kilometers, but was, in fact, much, much shorter. And that is exactly what happens. From the muon's point of view, it is stationary, and the entire atmosphere of the planet Earth is rushing up towards it at nearly the speed of light. And because of this immense relative velocity, the muon observes the entire vast thickness of the atmosphere to be dramatically compressed, or length contracted, in its direction of motion. The journey that we, on the ground, measure to be a long and difficult one of many kilometers, the muon, in its own reference frame, measures to be a short and simple sprint of only a few hundred meters, a distance it can easily and comfortably cross before its brief life comes to an end. Here we can see the true, breathtaking beauty of relativity. We have one single, undisputed event. The muon arrives at the surface of the Earth. But we have two completely different, yet equally correct, explanations for how it happened. The observer on the ground explains the event using the language of time dilation. The observer on the muon explains the very same event using the language of length contraction. Neither perspective is more true or more real than the other. The reality of the situation depends entirely on how you are moving. Space and time are not the fixed and rigid stage of Newton's dreams. They are a single, interwoven, and flexible fabric, space-time. And this fabric gracefully stretches and shrinks, its very geometry changing for each observer, all to perform the sacred and mysterious task of protecting the one true cosmic absolute, the speed of light. We have now learned the two great, new, and beautiful rules of travel in our relativistic universe. We have discovered that time is a personal, flowing stream that slows down as we move faster, and that space is a flexible, woven fabric that contracts in our direction of motion. These two effects, time dilation and length contraction, work in perfect and beautiful harmony. For a traveler on a journey at a significant fraction of the speed of light, the journey would seem much shorter in duration, and the distance to their destination would seem much shorter in length. It seems, at first, that the universe has given us a beautiful and elegant set of cheats to make the dream of interstellar travel a possibility. If we could just build a ship that could go a little faster and a little faster still, we could make our journeys as short as we liked. So the question returns with a new sense of urgency. What is stopping us from pushing that accelerator just a little bit more? What is stopping us from reaching that 100% mark, and perhaps even pushing beyond it? The answer is that the universe, while it allows for the beautiful bending of its rules, has also erected a final and absolute barrier at the very edge of the speed of light, a wall that becomes infinitely high at the very last moment. This great and insurmountable barrier is a direct and profound consequence of the single most famous equation in the history of science, another of Einstein's revelations from his miracle year of 1905. That equation, of course, is E equals mc squared. We have all seen this small, elegant line of symbols. We most often associate it with the immense and terrifying power of atomic energy. But its true meaning is far deeper, quieter, and more fundamental than that. It is a profound statement about the very nature of reality. What Einstein discovered is that energy and mass are not two separate and distinct things. They are, in fact, two different forms of the very same underlying substance. Mass, in this new view, is a kind of incredibly concentrated or congealed form of energy, and energy, in turn, has a kind of weight or inertia to it, a mass-like quality. They are like ice and liquid water, two different states of the same essential thing. And this deep and beautiful equivalence of mass and energy is the key to understanding why the speed of light is an absolute and unbreakable barrier. Let us think about the simple act of acceleration. In our everyday world, to make an object move faster, we have to apply energy to it. This is what we call kinetic energy, the energy of motion. In the old Newtonian universe, when we give a push to a shopping cart, we are simply adding kinetic energy to increase its speed, while its mass remains constant. But in Einstein's new and more precise universe, something else is also happening. When we add kinetic energy to that cart, we are not just increasing its speed, we are also, in a very real and physical way, increasing its mass. At the incredibly slow and gentle speeds of our human world, this effect is so infinitesimally small that it is completely and utterly undetectable. The extra mass that a commercial jetliner gains by flying at 600 miles per hour is less than the mass of a single eyelash. For all practical human purposes, Newton's idea of a constant mass is a nearly perfect approximation. But as we begin to accelerate our imaginary spaceship to speeds that are a significant fraction of the speed of light, this tiny, almost irrelevant effect begins to become the most important and dominant feature of our journey. Let us imagine we are in our powerful spacecraft. We ignite our engines, and we begin to accelerate. At first, for a given amount of thrust from our engines, we get a large and satisfying increase in our speed. We are pushing through the lower percentages of light speed. But as we get faster and faster, we begin to notice something strange. The same constant powerful push from our engines begins to produce less and less acceleration. It would feel as if our spaceship is becoming heavier, more sluggish, and more difficult to push. And from the perspective of an observer watching us from a stationary point, like the Earth, that is exactly what is happening. The immense amount of energy that we are pouring into our ship is no longer primarily going into increasing our speed. A larger and larger fraction of that energy is instead being converted directly into mass. As we cross the great relativistic thresholds, this effect becomes dramatic and then overwhelming. At about 87% of the speed of light, the relativistic factor gamma has already doubled. At 99.9%, gamma is more than 22, and as we continue to push, getting closer and closer to that final 100% mark, 99.999, and so on, gamma approaches infinity. And here, at last, we have arrived at the great and insurmountable wall. To accelerate an object whose relativistic factor tends to infinity would require an infinite amount of energy. There is not enough energy in our entire vast observable universe to give a single grain of sand that final infinitesimal push to make it reach the speed of light. The universe, in its deep and elegant wisdom, protects its sacred speed limit with a barrier of infinite energy. It is the ultimate law of diminishing returns. The first reason we cannot travel faster than light is because the price of admission, at the very last moment, becomes an infinite one. We have arrived at the great and absolute wall at the end of acceleration. We have learned that the universe, through the beautiful and profound logic of E equals mc squared, protects its sacred speed limit with a barrier of infinite energy. The dream of simply pushing a spaceship faster and faster until it reaches and surpasses the speed of light is an impossible one. The price of that final burst of speed is an infinite one. And the universe does not allow such a transaction. This is the great physical barrier. But the story of traveling at relativistic speeds has other, even stranger layers to it. Let us, for a moment, set aside the problem of infinite energy. Let us imagine that we could somehow build a ship that could approach this ultimate speed. What would this incredible journey actually look like? What would a human being, peering out of the cockpit window, truly perceive as they moved at 99.9% of the speed of light? The answer is that the universe would transform itself into a spectacle far stranger, more abstract, and more beautiful than any science fiction has ever depicted. The first and most powerful of these visual transformations is a phenomenon known as the aberration of starlight. This is a direct and simple consequence of the fact that light travels at a finite speed. We can understand it with a very simple analogy. Imagine you are standing perfectly still in a gentle rainstorm, where all the raindrops are falling perfectly vertically, straight down. The rain falls on the top of your head and your shoulders. Now, imagine you begin to run. Suddenly, from your perspective, the rain is no longer falling straight down. It seems to be coming at you from an angle, from the front, hitting you in the face. The faster you run, the more the rain seems to come from directly in front of you. The raindrops themselves have not changed their direction, of course. It is your own forward motion that has altered your perception of their trajectory. Exactly the same thing happens with the light from the stars. When we are here on Earth, moving relatively slowly through the cosmos, the light from the stars seems to come from their fixed, familiar positions in the sky. But as our imaginary spaceship accelerates, our own forward motion causes the apparent source of this light to shift. The light from the stars that were once off to our sides, or even slightly behind us, would appear to bend and migrate towards our direction of travel. As we accelerate closer and closer to the speed of light, this effect would become extreme. The entire, vast, 360-degree view of the universe would begin to crowd and compress into a small, brilliant, forward-facing cone of light. Everything, the great spiral of the Andromeda Galaxy, the familiar shape of the Orion constellation, the faint, distant smudges of countless other galaxies would all be visually squeezed into this compact tunnel. The rest of the sky to our sides and behind our ship would appear nearly starless and extremely dark, with any remaining starlight redshifted beyond human vision. It would feel as though we were flying down a long, dark, and infinite tunnel towards the single bright point of light that is our destination. The second great transformation would alter the very color and energy of this light. This is the relativistic Doppler shift. We are all familiar with the Doppler effect for sound. When an ambulance with its siren blaring approaches you, the sound waves are compressed, and you hear a high-pitched sound. As it passes you and moves away, the sound waves are stretched out, and you hear a low-pitched sound. The very same thing happens with light waves. The light from an object that is moving towards us at high speed is compressed, shifting its color towards the high-energy blue end of the spectrum. This is called a blue shift. The light from an object that is moving away from us is stretched, shifting its color towards the low-energy red end of the spectrum, a redshift. At the almost unimaginable speeds of our journey, this is not just a subtle change of color. It is a violent and extreme transformation of the nature of the light itself. Let us look first at the brilliant tunnel of light in front of us. The light from all of these stars and galaxies would be so intensely blue-shifted that their familiar, visible light would be pushed completely off the scale of what our eyes can see. It would be shifted up into the high-energy, invisible parts of the spectrum, first the ultraviolet, then the X-rays, and as we approached the speed of light, into the deadly, high-frequency gamma rays. The beautiful window of stars would become a single, blinding, and featureless point of white-hot lethal radiation. To our eyes, all the color and detail of the universe in front of us would be erased, replaced by a single, terrifyingly bright star. Now let us consider the universe behind us. Any faint starlight that was coming from that direction would be subject to an equally extreme redshift. Its visible light would be stretched out, down into the low-energy, invisible parts of the spectrum. It would become first infrared, then microwaves, and then finally long, cool radio waves. So the sky behind us would not only be empty of stars because of the aberration effect, it would also be completely and totally dark, as any light from that direction would be rendered invisible to our eyes. The final, combined view from the cockpit of a relativistic starship would be one of profound and absolute sensory deprivation. The familiar science fiction image of stars streaking past like lines of light is a complete fantasy. The true experience would be like flying through a perfect, silent, and infinite blackness, aimed at a single, star-like point of lethal white light, a point that contains the compressed and transformed image of the entire universe that lies before you. We have now explored the great physical and perceptual barriers that stand between us and the dream of traveling at the speed of light. We have learned that the universe protects its sacred speed limit with a wall of infinite energy, a price that can never be paid. We have also seen how the universe transforms our very perception of it as we approach this limit, compressing all of reality into a single, blinding point of light. These are the immense, practical challenges that make a journey to the speed of light an impossibility. But now, we must explore the final and by far the most profound reason that this barrier must exist. It is a reason that has nothing to do with energy or with perception, but with the very logical foundation of reality itself. The universe, it seems, forbids faster-than-light travel not just because it is physically difficult, but because it is logically impossible. The speed of light is not just a physical law. It is the great guardian of the sanity of the cosmos. To understand this, we must first become familiar with the most fundamental rule of our everyday experience, a rule so basic that we never even think to question it. This is the principle of causality. It is the simple and unshakable law that the cause must always precede the effect. A glass falls from a table, and then it shatters on the floor. A flash of lightning illuminates the sky, and then, a few moments later, we hear the clap of thunder. The past influences the present, and the present influences the future. This one-way, irreversible flow of events, this arrow of time, is the very foundation upon which our entire coherent reality is built. It is the basis of memory, of logic, and of our ability to make sense of the world. And the strange and beautiful truth is that faster-than-light travel would not just violate a law of physics, it would shatter the law of causality itself. The bridge that connects faster-than-light travel to this logical paradox is one of the strangest and most subtle consequences of Einstein's theory, the relativity of simultaneity. We have learned that time is personal, that it flows at different rates for different observers. A strange extension of this is that the very concept of two things happening at the same time is also not absolute. It depends on how you are moving. Let us return to our imaginary train. Imagine the train car is very long, and a light bulb flashes in the exact geometric center of the car. For a passenger sitting in that car, the light from that flash will travel outwards and will strike the front wall and the back wall at the exact same instant. For this passenger, the two events, the light hitting the front wall and the light hitting the back wall, are perfectly simultaneous. But now let us watch this event from the platform as the train is speeding past. From our stationary perspective, we see the flash of light happen in the middle of the car. But the back wall of the train is moving towards the point where that light was emitted. And the front wall of the train is moving away from that point. Since the speed of light must be the same for us as it is for the passenger, we on the platform will see the light reach the back wall before it reaches the front wall. Two events that were perfectly simultaneous for the passenger on the train are not simultaneous for us on the platform. This is a real physical effect. It proves that the universe has no universal now. The present moment is a personal and not a universal experience. And this strange, flexible nature of now is what opens the door to logical chaos, if the speed of light can be broken. If any information-carrying signal could propagate faster than light, then, because simultaneity is relative in Einstein's universe, it would be possible to send a message to one's own past. Imagine you are on a spaceship 1 light year away from Earth, and you send such a message back home, which arrives almost instantly. Because of the relativity of simultaneity, another observer, one who is flying past the Earth at a very high speed, could witness this sequence of events in a different order. From their reference frame, your message might arrive at Earth before you have even sent it from your spaceship. The effect could, in a very real, physical sense, precede the cause. This leads directly to the most famous of all logical paradoxes, the grandfather paradox. If you can send a message to your own past, you could, for instance, send a message to your younger self, telling them not to go to the party where your grandparents are destined to meet. If you successfully prevent them from meeting, then you will never be born. But if you are never born, then you could not have existed in the future to send the message back in the first place. It is a perfect and unbreakable loop of logical contradiction, a short circuit in the very wiring of reality. The universe simply cannot contain such a paradox and remain a coherent, logical place. And so, we arrive at the deepest and most profound reason for our cosmic speed limit. The speed of light is not just a physical barrier. It is the great firewall that protects the past from the future. It is the ultimate law that ensures the story of the universe unfolds in a rational and meaningful way. The universe, it seems, prefers all the strange and wonderful consequences of relativity. The slowing of time, the shrinking of space, the barrier of infinite energy, to the absolute logical anarchy that would be unleashed if a single object were ever allowed to break this one sacred and most fundamental law. We have arrived at what seems to be a firm and final conclusion. Our journey in search of a path to travel faster than light has led us to a series of great and insurmountable walls. We have met the physical wall of infinite energy, the perceptual wall of a reality that distorts itself into a single blinding point, and the ultimate logical wall of causality, which protects the very sanity of time itself. The laws of Albert Einstein's special theory of relativity. The rulebook for a universe with a constant speed of light appear to be absolute. They have closed every door and locked every gate. The beautiful dream of the starship, the hope of journeying to other worlds in a single lifetime, seems destined to remain forever in the gentle, forgiving realm of science fiction. If we are limited to traveling through space, then the speed of light is and will always be the final and unbreakable speed limit. But the story of Albert Einstein and the story of our universe does not end there. The special theory of relativity, as revolutionary as it was only the first act in his redrawing of the cosmos. For 10 more years, he worked to incorporate the force of gravity into his new vision of reality, and the result was his masterpiece, a theory of breathtaking beauty and power known as the General Theory of Relativity. And within the strange and wonderful new rules of this theory, within the elegant and complex mathematics that describe a much more dynamic and flexible universe, we find a new and profound kind of hope. General relativity does not break the sacred laws that we have just established. Instead, it reveals that the very fabric of reality is far stranger and far more malleable than we had ever imagined. And within that malleability, we may just find a loophole. To understand this new hope, we must first understand the fundamental difference between Einstein's two great theories. If special relativity is the rulebook for how objects move on a flat, rigid, and unchanging stage, then general relativity is the story of how the stage itself can bend, curve, stretch, and warp. In this grander vision, space and time are not a passive background. They are active and dynamic participants in the cosmic drama. The core idea is as simple as it is profound. Mass and energy tell space-time how to curve, and the curvature of space-time tells mass and energy how to move. This curvature, this geometry of space-time, is what we experience as the force of gravity. A great star does not pull a planet with an invisible rope. It creates a deep and graceful curve in the space-time around it, and the planet is simply following the straightest possible path through that curved space. And in this revelation, we find our new possibility. The sacred law of special relativity still holds true. Nothing can ever travel through a local patch of space faster than the speed of light. That speed limit is absolute. However, General relativity tells us that space itself is a flexible, dynamic thing. And here is the great loophole. While there is a strict limit on how fast you can move through space, there is no known limit on how fast space itself can move, or how it can be bent or warped. If we could somehow become engineers of the fabric of space-time itself, we might be able to create shortcuts, ways to cheat the law without ever technically breaking it. Let us imagine a simple analogy. Picture a small, patient ant standing on a large, flat Persian rug. The ant wants to get to a crumb of food on the far side of the rug. It begins to walk, and it is limited by its own personal top speed. This is like a spaceship traveling through space, limited by the speed of light. To the ant, the journey is a long and arduous one. But now, imagine that we, as higher dimensional beings, can interact with the rug itself. We can take the far end of the rug, where the crumb is, and the end where the ant is, and we can simply fold the rug over, bringing the two ends almost completely together. Now, the ant can simply take one small step from one end of the rug to the other, reaching its destination almost instantly. The ant never, for a single moment, exceeded its own top speed. It never broke its own personal speed limit. But by taking a shortcut through a higher dimension, by taking advantage of the folded geometry of its universe, it has completed the journey in a fraction of the time. This is the new dream that general relativity offers. It is the dream of becoming not just travelers on the cosmic rug, but of becoming the weavers who can fold it to our will. This idea that space-time can be bent and folded is not a mere fantasy. It is a direct consequence of the mathematics that so perfectly describes our universe. And within the complex solutions to Einstein's great equations, physicists have found several strange, ghostly, and tantalizing possibilities that look, for all the world, like cosmic shortcuts. They are the theoretical possibilities that have fueled a century of science fiction. They are the beautiful and perhaps impossible dreams of wormholes and warp drives. We have, at last, found a new path in our journey. We have discovered that if we wish to travel to the stars, we should not be trying to build a faster engine. We should be trying to build a more elegant map. We have arrived at a moment of new and quiet hope in our long journey. The rigid, unbending laws of special relativity, which seem to close the door forever on our dream of faster-than-light travel, have been softened by the grander, more flexible vision of general relativity. We have learned that while the local speed limit of light is sacred and absolute, the very fabric of space-time itself is a dynamic and malleable entity. And in this flexibility, we have found a new and audacious dream. It is the dream of not breaking the law, but of bending it. It is the dream of the cosmic shortcut. We are no longer trying to build a faster ship, but to weave a more elegant map of the cosmos. And the first and most famous of all the strange and beautiful shortcuts that appear in the mathematics of Einstein's universe is a concept that has captivated our imaginations for a century. It is the idea of the wormhole. The official, more scientific name for a wormhole is an Einstein-Rosen bridge, and it is, in its essence, a theoretical tunnel through the fabric of space-time. To understand this beautiful and mind-bending idea, let us return to our simple analogy of the Persian rug. Imagine that our vast three-dimensional universe is the flat, two-dimensional surface of this rug. To get from a point A on one side to a point B on the other, a journey of many thousands of light years, a spaceship would have to travel a long and arduous path across the surface of the rug. This is the journey that is limited by the speed of light. But now, let us imagine that we could gently fold this great cosmic rug through a higher, unseen dimension, bringing the location of point A and point B very close together. A wormhole is the theoretical tunnel, the throat that would directly connect these two now adjacent points. It would be like poking a small pencil through the folded fabric of the rug, creating a direct passage from one side to the other. A journey that might have taken 100,000 years by traveling through normal space could, by passing through the throat of the wormhole, be completed in a matter of hours, or even minutes. And the beautiful thing about this idea is that at no point would our spaceship ever be breaking the local speed limit. As it traveled through the throat of the wormhole, it would still be moving at a speed well below the speed of light. But by taking this extraordinary shortcut, its effective speed between its starting point and its destination would have been almost unimaginably vast. It would not have broken the law. It would have, in a sense, risen above it, using a deeper understanding of the geometry of reality to its advantage. The visual experience of encountering a wormhole would be just as strange and beautiful. From the outside, the mouth of a wormhole would likely not look like a tunnel at all. It might appear as a perfect, shimmering, and completely silent sphere, a place where the space around it seems to be distorted, like looking through a crystal ball. And as you got closer, you would not see a long, dark tunnel stretching out before you. You would see, through this spherical gateway, a direct, albeit strangely warped view of your destination. You would see the stars and the sky of a place that is thousands of light years away, as if you were looking through a cosmic doorway. This idea is not a pure invention of science fiction. It emerges, naturally and ghost-like, from the very mathematics of general relativity itself. The original Einstein-Rosen bridge appeared as a feature in the mathematical solution that describes the intense curvature of spacetime at the heart of a black hole. In this original vision, the entrance to the wormhole was a black hole, a place where you can only fall in, and the exit was a theoretical and opposite object called a white hole, a place from which things can only come out. It was a beautiful, but purely mathematical curiosity. And for a long time, that is all it remained, because as physicists studied these mathematical bridges more closely, they discovered a series of immense and perhaps insurmountable problems. The first and most devastating problem is that of instability. A simple Einstein-Rosen bridge, as described by the equations, is an incredibly ephemeral and transient thing. The throat of the wormhole, the very tunnel that a traveler would need to pass through, would pinch off and collapse into an infinitely dense singularity the very instant that it formed. It is a bridge that collapses and disappears the moment you try to take your first step upon it. It is a doorway that slams shut the instant a single particle of light tries to pass through it. To solve this problem, to find a way to prop the throat of the wormhole open long enough for something to travel through it, physicists discovered that you would need to line it with a truly bizarre and hypothetical substance, a material with properties unlike anything we have ever observed in our universe. This substance is known as exotic matter. All the matter and energy we know of, the stuff that makes up stars, planets, and ourselves, has a positive mass and a positive energy density. Its gravity is attractive. It pulls things together. To stabilize a wormhole, you would need a substance that has a negative mass or a negative energy density. This exotic matter would have a kind of anti-gravity. It would be gravitationally repulsive. It would act as a kind of cosmic scaffolding, pushing the walls of the wormhole's throat outwards and preventing its catastrophic collapse. We have no evidence that such a substance can or does exist in our universe. Its very existence would seem to violate some of the most fundamental and well-tested principles of physics. And so, the beautiful dream of the wormhole, this elegant and poetic shortcut through the cosmos, remains for now just that, a dream. A ghost in the machine of relativity, a beautiful and tantalizing what-if, a testament to the strange and wonderful possibilities that lie hidden within the deep, geometric heart of our universe. We have just journeyed through the strange and contorted corridors of a theoretical wormhole, the first great shortcut to emerge from the deep mathematics of Einstein's general relativity. We have seen how this bridge through spacetime, this elegant doorway to the stars, offers a beautiful and poetic solution to our dream of faster-than-light travel. But we have also found that this doorway appears to be locked, guarded by the immense and perhaps insurmountable barriers of instability and the need for an impossible, otherworldly ingredient known as exotic matter, a substance with the strange property of repulsive gravity. The wormhole, for now, remains a ghost in the mathematics, a beautiful dream from which we have not yet found a way to awaken. But the flexibility of spacetime, the central lesson of general relativity, is a deep and generous idea, and within its elegant equations, it offers us another possibility, another theoretical shortcut, one that is, if anything, even stranger and more elegant. Instead of punching a tunnel through the universe to shorten the journey, what if we could bring our destination to us? This is the astonishing idea that lies at the heart of the second great dream of interstellar travel, the warp drive, also known as the Alcubierre drive. Proposed in the year 1994 by the Mexican physicist Miguel Alcubierre, the warp drive is a mathematically valid solution to Einstein's field equations. The concept is a masterpiece of ingenuity, and it bypasses the cosmic speed limit in a wonderfully clever way. The key, as we have learned, is that the speed of light is the limit for any object moving through space, but there is no known limit to the speed at which space itself can expand or contract. Indeed, we believe that during the period of cosmic inflation in the first instant after the Big Bang, the universe itself expanded at an immensely superluminal rate. The Alcubierre drive seeks to replicate this effect on a local and controlled scale. Let us imagine our spaceship, floating in the silent void. Instead of firing its engines to propel itself forward, the ship activates its warp drive. This theoretical device would, in principle, create a small bubble of perfectly normal, flat spacetime around the ship, protecting it from any strange forces. Inside this bubble, the ship would be essentially at rest. It would not be moving at all, but at the same time, the drive would radically deform the fabric of spacetime around the bubble. The drive would cause spacetime to violently contract in front of the bubble, and just as violently to expand behind it. The most helpful analogy is that of a surfer on a wave. The surfer is not moving through the water by swimming. They are standing still on their board, at rest relative to the wave itself. But it is the wave, the disturbance in the water, that is carrying them at great speed towards the shore. The starship with an Alcubierre drive is the surfer. It remains safe and still in its small, local bubble of spacetime, never once moving faster than light within that bubble. But the wave of spacetime in which it is riding, the bubble itself, is propelled forward by the pulling action of the contracting space in front and the push-in action of the expanding space behind. The ship, in essence, is riding a self-generated wave of pure spacetime. From the perspective of an outside observer, this bubble and the ship nestled safely inside it could travel at an effective speed hundreds or thousands of times greater than the speed of light, allowing for journeys to the nearest stars in a matter of weeks or months, rather than millennia. And because the ship is at rest inside its bubble, the crew would experience none of the extreme forces of acceleration, nor the strange effects of time dilation that are associated with conventional relativistic travel. It is, in theory, the perfect way to travel the stars. A calm, smooth, and mere instantaneous journey with none of the bizarre side effects of moving through space at high speed. However, just like the wormhole, the Alcubierre drive faces obstacles so immense that they place it firmly in the realm of theoretical science fiction. And the problem is exactly the same impossible guardian at the gate of the shortcut, the need for exotic matter. In order to achieve the incredible feat of contracting space-time in front and expanding it behind, one would require a density of negative energy. We would need, once again, a material with repulsive gravity to inflate the space behind the ship. And not just a small amount. Alcubierre's original calculations suggested that for a small, ship-sized bubble, an amount of negative energy equivalent to the mass of the planet Jupiter would be required. While more recent and efficient bubble designs have reduced this astronomical figure, the amount of energy needed is still colossal, and it is of a nature that, as far as we know, does not exist. Furthermore, the warp drive presents other, equally strange theoretical problems. It seems that it would be impossible to start the bubble from within the ship itself. It would have to be created by some external infrastructure. And more alarmingly, upon arriving at its destination and turning off the drive, the release of the energy that was accumulated at the front of the bubble could be catastrophic, unleashing a blast of high-energy radiation capable of annihilating anything that was in its path. The warp drive, therefore, tells us the same story as the wormhole. General Relativity is like a complex book of cosmic laws, and in its fine print, there appear to be certain clauses that would, in theory, allow one to bypass the primary law forbidding faster-than-light travel. But each of these clauses comes with a requirement, the existence of exotic matter, that appears to be forbidden by other, perhaps even more fundamental laws of physics. They are tantalizing shortcuts, but the toll required to use them seems to be an ingredient that the universe does not possess. We have just journeyed through the two most beautiful and tantalizing dreams in all of science fiction, the great theoretical loopholes of general relativity. We have imagined stepping through a shimmering spherical gateway, a wormhole, to arrive in a distant star system in an instant. We have imagined our starship resting peacefully in a bubble of space-time, riding a self-generated wave of reality to its destination at a speed of thousands of times that of light. These two ideas, the Einstein-Rosen bridge and the Alcubierre warp drive, are breathtaking in their elegance and in their promise. They are the ghosts in the machine of Einstein's mathematics, whispering to us that the great cosmic prison of the speed of light may not be as inescapable as it first appeared. And yet, both of these beautiful, hopeful dreams, when we examine them with the cold, hard light of our known physics, run headfirst into the very same, seemingly insurmountable wall. They both require, for their very existence, a single, impossible ingredient. It is time for us to now, in the quiet of our journey, become acquainted with this great gatekeeper of our faster-than-light dreams. It is a substance known as exotic matter. To understand what makes this material so exotic, we must first take a quiet moment to appreciate what makes the matter of our own universe so wonderfully normal. Every single thing that we have ever seen, touched, or measured in the cosmos, from the smallest grain of sand to the largest supercluster of galaxies, from the heat of a candle flame to the light of a distant star, is made of what we can call normal matter and energy. And the single, defining characteristic of all of this normal substance is that it has a positive energy density. This positive energy is what gives matter its familiar property of mass, or inertia. And according to the laws of general relativity, it is this positive energy density that causes the fabric of space-time to curve in the way that we experience as gravity. Positive energy creates an attractive gravitational force. It is the force that pulls things together. It is the gentle but insistent force that holds you to your bed, that holds the Earth in its orbit around the Sun, and that holds the great galaxies together against the rush of cosmic expansion. Exotic matter, the impossible ingredient required to build a wormhole or a warp drive, would have to be the exact opposite. It would be a theoretical substance that has a negative energy density. This is a concept so strange that it is difficult for our minds to even grasp. The most profound and bizarre consequence of this property is that this exotic matter would have a kind of repulsive gravity. It would curve spacetime in the opposite direction. Instead of pulling other matter and energy towards it, it would actively and powerfully push it away. It would be the truest and most literal form of anti-gravity. And now we can understand why this strange substance is so essential for our FTL dreams. In the case of a wormhole, this repulsive gravity would be needed to act as a kind of cosmic scaffolding. It would have to be used to line the throat of the wormhole, pushing the walls of spacetime outwards and preventing the tunnel from instantly collapsing in on itself. In the case of the Alcubierre warp drive, this repulsive gravity would be the very engine of the ship. It would be needed to create the violent and continuous expansion of spacetime behind the warp bubble, the great pushing wave upon which the ship would ride. Without this gravitationally repulsive negative energy substance, both of these beautiful mathematical solutions simply cannot exist in the physical world. This, of course, leads us to the great and crucial question: does this exotic matter, this substance with a negative energy density, actually exist in our universe? The answer, on the grand macroscopic scale of our daily lives, is a firm and unambiguous no. Every object we have ever observed follows the familiar rules of attractive gravity. The laws of physics as we understand them, a set of principles known as the energy conditions, essentially forbid the existence of large, stable quantities of this kind of matter. But the story, as it so often does in physics, becomes a little stranger and more wonderful when we zoom down into the microscopic quantum realm. In the strange and counterintuitive world of quantum mechanics, there is a real, measurable, and deeply strange phenomenon known as the Casimir effect. If you take two perfectly flat, uncharged metal plates and place them incredibly close together in a perfect vacuum, a strange thing happens. They are gently pushed together by an invisible force. The reason for this, as we have learned, is that the quantum vacuum is not empty. It is a seething sea of virtual particles. The tiny, microscopic gap between the two plates restricts the kinds of virtual particles that can pop into existence there, while the infinite space on the outside of the plates can host all kinds of them. This creates a tiny imbalance, a pressure from the outside that is stronger than the pressure from the inside, which pushes the plates together. And the strange and beautiful thing is that the region of space-time between the two plates can be described in a very real, physical sense as having a slightly negative energy density relative to the vacuum around it. For a fleeting moment, in a microscopic space, we have created a whisper of the exotic energy we would need. But this tiny, fleeting glimmer of hope is for now all that it is. The leap from creating a microscopic, transient, and incredibly faint negative energy effect between two plates to gathering and stabilizing a planet-sized mass of this substance to build a warp drive is a leap that most physicists believe is fundamentally impossible. It seems that the universe, in its deep wisdom, may allow you to borrow a tiny amount of negative energy from the quantum void for a brief moment, but it has very strict rules that seem to prevent you from ever accumulating enough of it to do anything on a large, macroscopic scale. And so we find ourselves at the end of our journey through the great loopholes. We have found that the beautiful geometries of wormholes and warp drives are mathematically possible in the language of general relativity, but the very substance required to build them seems to be forbidden by the even deeper and more fundamental language of quantum mechanics. Our long and quiet journey is now nearing its final destination. We have traveled from the common sense, clockwork universe of Isaac Newton to the strange and beautiful, flexible reality of Albert Einstein. We have accelerated our imaginary ship to the very edge of the speed of light and witnessed time slow down, space contract, and the universe itself distort into a single brilliant point. We have found the great insurmountable walls that stand in our way, the physical wall of infinite energy, and the even more profound logical wall of causality. And then, in a final surge of hope, we journeyed through the speculative, theoretical loopholes of general relativity, the beautiful dreams of wormholes and warp drives, only to find them guarded by the impossible price of an ingredient that the universe itself seems to have forbidden. We have followed every path, explored every possibility, and now it is time to deliver the verdict. It is time to answer the simple and ultimate question with which we began our journey. Based on everything we currently understand about the deep and fundamental laws of our cosmos, the answer to the question, can you travel faster than light, is a quiet, a gentle, and an unambiguous no. The speed of light is not just a technological challenge to be overcome. It is not just a guideline. It is a fundamental and structural pillar of the reality we inhabit. The universe is built upon this law, and it protects it with a beautiful and interconnected series of other laws. It is a physical impossibility because it would require an infinite amount of energy, and it is a logical impossibility because it would unravel the very fabric of cause and effect, turning the coherent story of the universe into a chaos of paradoxes. The dream of accelerating a ship past the speed of light seems to be, and will likely forever remain, a dream. And this conclusion, at first, can feel like a profound and sorrowful one. It can feel like a great cosmic confinement. It seems to place our species, and any other species that may exist in the galaxy, into a kind of prison, confined for our entire existence to our own, small, local star systems by the unbreakable, invisible bars of the speed of light. The great, star-filled vistas of science fiction, the dream of a galactic empire, of meeting other civilizations, of exploring other worlds, all of this seems to be rendered an impossible fantasy. But now, in the final stages of our journey, let us re-examine this prison. Let us look at its walls, not with a sense of confinement, but with a new and deeper sense of perspective. For this great cosmic prison is also, in a very real sense, our beautiful and quiet sanctuary. This cosmic speed limit offers one of the simplest and most powerful possible solutions to the great and haunting mystery of the Fermi paradox, the question we call the Great Silence. Why, in a galaxy of billions of stars and billions of years of history, have we seen no evidence of any other intelligent life? One plausible answer is that the speed of light is not just a local law, it is a universal one. The same unbreakable physical and logical barriers that keep us confined to our own solar system also confine every other potential civilization to theirs. In this view, the galaxy is not an empty and silent empire, waiting for a conqueror to arrive. It is instead a vast and beautiful archipelago, a collection of countless, isolated, and unique islands of life, each one separated from the others by an ocean of space and time, so vast and so profound that by the very laws of physics, it is almost completely uncrossable. And this great cosmic isolation may in fact be a form of protection. Imagine for a moment a universe where faster-than-light travel was simple and easy. The history of the galaxy might not be a quiet and peaceful one. It might be a story of conflict, of conquest, of colonization, a story where the first civilization to achieve this great technological leap could dominate all the others. The speed of light in our universe acts as a great and silent quarantine. It ensures that every one of these beautiful islands of life is allowed to evolve on its own, in peace, without the threat of interference from the outside. It is a law that protects the vast and precious biodiversity of the cosmos. The great silence of the universe, from this perspective, is not the silence of an empty and lonely room. It is the respectful, peaceful, and life-giving silence of a great and ancient library, where every story is allowed to unfold undisturbed. Finally, and most personally, this beautiful prison forces us to turn our gaze back towards our own home. If we can never truly leave to find a planet B among the stars, it radically and permanently increases the value and the preciousness of our own world. The dream of escaping our problems by conquering a new frontier is revealed to be a fantasy. Our entire destiny, the whole of the human story, both past and future, is tied to the health and the survival of this one, single, fragile, and irreplaceable island of life. The speed of light, the great cosmic law, is also the ultimate environmental message. It is a quiet, constant, and profound reminder from the universe itself to take care of our beautiful and our only home. Our long and quiet journey to the edge of the speed of light has now reached its peaceful conclusion. We began with the grand and fiery dream of breaking the one ultimate law of the cosmos, of traveling faster than light to reach the distant stars. And we have returned instead with a deep, gentle, and profound understanding of why this beautiful barrier must exist. We have learned that the speed of light is not a prison wall, but a fundamental pillar that upholds the very logic of our universe. It is the great guardian of cause and effect, the silent law that protects the orderly unfolding of time, and a quiet, steady metronome that has allowed for the patient 13.8 billion year story of our cosmos to be written. The answer to our question is clear, but the journey to that answer has revealed a universe far stranger, more beautiful, and more elegant than we could have ever imagined. And in this great cosmic law, there is one final and deeply personal message for us as we rest here on the shores of sleep. In our own lives, we so often feel the urge to rush, to accelerate, to move faster than the gentle, natural pace of our own unfolding story. We see our own limitations as barriers to be broken, and our own human speed as something to be overcome. But the universe, in its deep and patient wisdom, teaches us that there is a profound peace to be found in accepting our own natural rhythm. The great silent barrier of the speed of light is a cosmic reminder that not all barriers are meant to be broken. Some are there to give us structure, to give us a sense of time, and to allow for the slow, beautiful, and irreplaceable journey of simply being. And so now, our journey is complete. There are no more questions to ask, no more speeds to chase. All that is left is to rest in this quiet understanding. As you prepare now for your own gentle journey into the quiet of the night, you can carry this sense of cosmic peace with you. Let go of the rush and the acceleration of your day, and allow yourself to sink into the slow, steady, and natural rhythm of your own breathing. Allow yourself to travel at your own perfect speed, the gentle and healing speed of rest. The journey continues, always calmly, always at the pace of the universe.